Okay, good morning, Blinken. I hope you can all see me, see the presentation as well.
Yes, we can.
My name is my name is Felipe Arias, and I am part of the web platform team at Igalia. I work on Chromium and WebKit, and today I am going to be talking about support for richer colors in the web and how we could add that support to Chromium in the future. Now, talking about color, the study of color is very interesting because it brings together concepts from physics, how light works, from biology, how eyes see, and it also has a very rich history about color and the search for ways to use it to make art. For example, during the Renaissance, painters would go into depth to buy this pigment called ultramarine blue that was much more beautiful and vivid than the others. Ultramarine was created from the precious stone, semi-precious stone lapis lazuli, which was mined in the mountains of Central Asia and then imported to Venice and from there distributed across Italy and other countries. Which is just a way to say, as introduction, that the desire to have access to richer colors and richer materials when creating visual art goes back a very long way. In this talk, we will be talking about the ongoing efforts to specify richer colors on the web platform. We'll be talking about how Blink paints colors at the moment and what it would take for it to widen the range of colors that it is able to paint. We'll share some very early ideas about how to do that. And then we will have some time for questions and comments. And there I would like that people that have been working on this area already would give their own opinion and their own point of view. So starting with color on the web, traditionally, the web has been built on top of the standard RGB color space, which is a standard color space that was created in 1996. Basically, what it defines is the three color primaries, the red, green, and blue, and then a transfer function that is nonlinear and then links the numerical values with the intensity of those primaries for a given color. Is a way to specify the luminosity of the color space in a way. In the web, as I said, colors are specified in the sRGB color space, usually using a value between 0 and 255 for each channel, plus an opacity value. And as you can see in the examples below, there are a number of functions and shortcuts already in CSS to define a color in the sRGB space. Mention that it is a color space. A color space is basically just a way to describe and to organize colors. The one on the left is an important one. It's called the CIE XYZ, and it was specifically designed to cover all the colors that the average human can see from some research done all the way back at the beginning of the 20th century. And the second one, from that large map of colors within human perception, the second graph identifies the colors that fall within the sRGB color space, the colors that can be described using the sRGB primaries and functions. And as you can see, there are many colors that we actually can see, but you cannot specify in sRGB. We will come back to this graph in a moment. In the past years, there has been an increasing interest in adding support for richer colors in the web, in the different components in the web platform. There are many good resources about this here and throughout the presentation. I will just link to some articles that I found interesting. Here we have a couple of good ones about richer colors in CSS, which are, and basically this is how I got into this area, interested in this area in the first place. There are already several JavaScript libraries that provide functionality for manipulating colors, but are still limited by what the browser can actually display. In Chromium, there is now an intent to experiment with additional color spaces for Canvas, for WebGL, and for WebGPU. There is already support for images that indicate that they should be displayed on a color space other than standard RGB. So in this talk, I am going to focus specifically on adding support for richer colors defined in HTML and CSS. The reference specification for this is the CSS color module that is elaborated by the CSS working group. There is also a Color on the Web community group that organizes a workshop on white color gamut for the web. There is also a technical architecture group at the W3C that had an interesting discussion about how having colors outside of the standard RGB gamut open up questions about interoperability between the different elements of the web platform. And I am probably already unintentionally leaving somebody unmentioned, so I apologize ahead of time for that. And of course, this is all specifically about the web platform, leaving aside the many standard groups that already exist for video, multimedia, images, and so on. The CSS color spec, among other things, extends the color function in CSS to let the author explicitly indicate the desired color space of a color, including the color spaces with a much wider gamut. It defines the LAB and LCH functions to specify colors in the LAB color space, which is, as we will see in a moment, more predictable and homogeneous in terms of human perception. The spec provides detailed control over how interpolation happens and many other features. And it's a very long spec, and it's very interesting. For example, it already contains reference implementation for the transformations and operations describing it. From the discussion at the TAG group that I mentioned earlier, it seems that people are interested in implementing this new functionality along with the support for richer gamuts. So having the ability to paint richer colors and also the ability to manipulate those colors in a much more interesting, much more flexible way than what is available at the moment. So here are three reasons why this work is important. First, as we saw in the graph earlier, using only standard RGB limits the range of colors that can be displayed. Many modern displays, many mobile devices, for example, have a wider gamut, a wider range of colors that can be displayed. Usually, for example, close to another standard that's called display P3. And here you can see both of those color spaces over the same graph that we saw before. The display P3 space is about 1/3 larger than a standard RGB, which means that from CSS, we have no access to about 1/3 of the colors that modern monitors can display. And these are not just any colors, they are the most intense, the most vivid colors that the monitor can display. This is another visualization where the white line in each of the three squares represents the boundary between what can be described within standard RGB and what is inside display P3. So you can see that the colors already at the extreme are not reachable through standard RGB alone. Second reason is to have access to other color spaces, which, as I said, are ways of specifying colors, because standard RGB and HSL, which is a related way of specifying colors in the same standard RGB color space, they are not perceptually uniform. The same amount of change, the same number in a value, does not cause similar changes in the colors that we perceive. We can see this clearly with HLS, which expresses the colors in terms of the hue, the lightness, and saturation. And as you can see in the first example here, the same numeric amount of change in hue does not cause a similar change in the colors that we perceive in both cases. A change of just 20 degrees in hue in the first case is the difference between orange and yellow, and in the second is just a very similar blue. In the second example, we have two colors with the same saturation value, but that's obviously not how we perceive them. One looks a lot more saturated than the other. And the third example is similar, with two colors that are supposed to have the same lightness value, but we don't perceive them to have the same lightness value at all. This means that in general, standard RGB and HSL cannot be used to adjust the lightness, the saturation, the hue with good precision, and cannot be used to find complementary colors or to find accurate contrast between two colors. One of the new functionalities of the CSS color spec is to let you define colors in the LCH color space, where each color is defined by the lightness, the chroma or the amount of color, and the hue. And this is a uniform color space where the same numerical changes in one of the values brings similar perceived changes. In the first row, the same change in lightness brings a similar change in the lightness that we can see. Second row, the same change in the amount of color brings a similar change in the amount of color that we can see. And the third one, the same with the hue. And having these previous features in place already enables very interesting functionality. For example, when you have to interpolate between two colors because of, for a gradient or a transition, you can use different color spaces. You can find the path between those two colors in different color spaces, which will give you different results. And here are some examples of the transition between two colors in different color spaces in standard RGB and also HSL, LAB, LCH. Just to mention that the examples with HSL and LCH, because hue, they have hue in terms of degrees, the gradient interpolation has to pass through the different colors across those degrees, the separation in degrees. And there is already in the CSS Color 5 a way to specify exactly how this transition should happen. So you can have, as I have the example there, you can have one that goes from red to green passing through blue, and another one that goes from red to green passing through yellow. And of course, some of these options look more pleasing than others, but more than that, the point is that this functionality broadens the range of tools available to web designers when creating their sites. Now let's talk about Chromium as you know, it is the free software portion of the Chrome and Edge web browsers. The web engine of it is called Blink, which is the name of the conference. And Blink implements the web platform standards that describe how to turn web content into pixels on the screen. This is the Blink render pipeline. Blink basically creates a pipeline that takes web sources as input, as pages, style sheets, and so on, parses them, applies styles, defines the geometry, ranges the content into layers and tiles, paints those, and sends them over to be displayed. This job of actually painting those pixels is carried out by a multi-platform graphics library called Skia. In Chromium, there is already some color management. There is also support for media queries about the color capabilities of the display, support for embedded color profiles in images, and so on. But there isn't yet support for using richer color spaces with individual web elements. Within Blink, CSS colors are parsed and stored into a small structure, just 32 bits, that is 8 bits per RGB color channel plus alpha. And these colors are eventually handed over to the Skia library to carry out the actual drawing. Skia then uses its own similar 32-bit format, which means that throughout Blink's rendering pipeline, colors are represented using only 32 bits. And this limits the precision and the richness of the colors that can be used and displayed in websites. So if you want to see that in the rendering pipeline that we saw before, this is how it looks. We have a web page that specifies a color in RGB. And within the Blink main thread, within the Blink render process, this is stored in a 32-bit data element and passed across the different stages of the rendering process until it reaches Skia to be rastered and displayed. And Skia uses its own similar data format until eventually the color is displayed on the screen. So to get some ideas about how we could overcome this limitation and evolve color support in Chromium, we could look at WebKit. As you know, Blink started as a fork of WebKit in 2013. And although they have evolved in different ways, we can still look at WebKit to get some inspiration for storing and manipulating high-precision colors. Without getting into too much detail, WebKit supports a high-precision representation of colors that stores 4 float values plus a color space, including LAB as one of those spaces that may be used to define colors. And having this support for higher precision colors has already made it possible to implement several color features in WebKit, like support for the P3 gamut and the LAB LCH CSS functions. And big difference between WebKit and Chromium is that WebKit uses the platform's graphic libraries directly, whereas Chromium uses Skia. And Skia is multi-platform. In the case of WebKit, because it uses the platform's own graphic libraries, also means that support for wider color gamuts is something that is not necessarily available in all platforms. So there is a clear trade-off between the two approaches. Now, looking at the Skia in particular, interestingly, Skia does not have the same limits in color precision and range as Blink does. Internally, it has a format for high-precision colors that holds 4 float values, and it's also able to take color spaces into account. And much of the Skia API is already able to take into a color space and 1 or more high-precision colors defined in it. So Skia is able to paint richer colors on hardware that supports them, which means that if we manage to get that rich color information defined in the web sources at the beginning of the pipeline all the way to Skia at the end of the pipeline, we would be able to paint those colors correctly on the screen. There's a couple of additional things worth mentioning here. First, Skia's representation of high precision colors still uses a format in terms of red, green, blue, alpha. So out of the box, it does not support other formats like LAB or LCH. Secondly, the CSS color spec, as I mentioned, provides ways to specify the interpolation color space for gradients, transitions, and so on. And Blink relies on Skia for this interpolation, but Skia does not provide fine-grained control. Skia will always use the color space where the source colors have been defined and does not support interpolating in a different space. So as a very broad summary, the first step to support wider, richer color gamuts in Blink is to parse the CSS code using including those new features. Those wide gamut colors and the color spaces need to be stored in a high precision format that can be used throughout Blink's rendering pipeline. At the end of the pipeline, it needs to be translated so Skia can paint those colors correctly in the desired hardware. And for this, we may also need more fine-grained control over interpolation and probably also other changes. And this work is not straightforward because it would touch a lot of different components, and it might also have an impact on memory, on performance, on how paint information is recorded and used, and so on. For web authors, it is important that these features are available at the same time so they can rely on the new functionality provided by the CSS color spec. And I hope that with this talk, you got a better understanding of the scope of the work that will be needed in Chromium. I see this as some of the first steps in a long road to increase the expressivity of the web platform and to widen the range of tools that are available to authors when creating the web. Thank you very much. Thank you also to the BlinkOn organizers for putting together this conference. And now I think we should have some time for questions, but I think I went over the time that I had budgeted. So I don't know if anybody has any quick comment that they want to add. Otherwise, I'm available on email, on Twitter. I'm going to put up a write-up of this talk in my blog. And yeah, I'm really interested to hear about people working in more detail on more aspects of this problem space, because I think it is a really good way of making the web a far more useful tool for designers and for creators. Thank you very much.
Cool. So if we do have time for a quick question, I wondered about the likely time frame of implementing some of these features.
I cannot answer that. I am still figuring out the problem space and the approach and the number of changes that would be necessary. As I mentioned, this has all sorts of impacts around the Blink platform. So I'm sure I can give a broad overview of the changes needed. I'm sure there will be a lot more detailed issues once we start looking into it.
Yeah, so just thinking about, whether, for example, Chromium would begin to implement that draft, or whether, or whether we're kind of looking at sort of next year for those features to start coming, as it were.
As far as I know, there's a lot of interest in this, but I don't know of any specific plans to implement it. I started researching it and doing some experiments last year, until it became clear that it was too big for just one contributor to do. I think it's doable, but I think planning the project and the steps still requires more time.
Cool. Okay, thanks.
Thank you. Any other questions or comments? Otherwise, I think we can close the session. Okay, thank you very much, everybody. Thank you very much for attending, and thank you to the BlinkOn organizers for putting together the conference. Thank you.